Just a quick recap of this notion of physical versus virtual addresses. I had already talked about it a little bit, but just want to sort of go over it again because it is an important thing to keep in mind in the context of DMA. The CPU uses virtual addresses. Usually there is hardware support inside the CPU such as the translation, look-aside buffer and so on, which allows us to find out what the translation is from physical to virtual, and the operating system plays a role in sort of managing that, right. The DMA on the other hand is outside the CPU. It does not get to see virtual addresses or does not know the mapping between a virtual address and a physical address, which means that the DMA needs to actually know physical addresses. And if you write code like this where you are basically sort of into the source address for an MM2S, if you use the virtual address, this is wrong. Basically what can end up happening is that the DMA is now going to generate addresses from this range which physically do not correspond to a location on the AXI bus. The translation is not happening on the bus, it is happening inside the CPU, and therefore things go wrong. You need to actually use the physical address itself, right? Which sort of brings us to this whole notion of how do you go about debugging issues related to DMA. If anything, this is even one step more complicated than IRQ related debugging, but there are a number of general rules of thumb to follow and general good practices. So this is sort of more, this is not exhaustive, this is just some common issues that you can face when you are working with DMA, right. If DMA stalls, it's very likely that your physical addresses are not valid, right. You are supposed to use the appropriate pointers when you are sort of passing data into the DMA functions and so on. If you find that the data you are getting is wrong, right, it could simply be because you did not allocate coherently, right. If you use kmalloc instead, it might work because you have still got addresses and so on, but on the other hand you cannot guarantee cache coherency, right. Of course it also leads to the issue that this kmalloc is, you can still sort of give it the physical address, but because you mallocked the buffer that was underlying it, right, it does not guarantee that the cache is being kept coherent with whatever is there in the outside memory. A common thing, not just for DMA but in general for any kind of IRQ related thing, is you didn't enable the IRQs, right. There's some kind of a control register for which you need to explicitly enable it. If you have not done that, the DMA is never going to signal completion. Partial transfers can happen because remember how the DMA IP has been set up to work. The moment you write something into the length register, it sort of goes ahead and starts the DMA, right. One other related thing that could sometimes happen is the fact that you could potentially get a T-last at the wrong time. Now, how exactly wrong time? Probably because there was some other part of the hardware that did not have the same idea of the size of the packet as what your original DMA thought it was supposed to be. So if the T-last comes early, the DMA basically terminates and says, okay, I have transferred all the data that was there, even though you were expecting something more, right? And well, this is not really a debugging issue. It's more that very often you might find that when you are allocating memory or you are using addresses for transferring data, you need to follow proper alignment of the addresses, right? Which could be either 4 bytes or it could be a complete cache line level alignment, right? In other words, a large chunk of data, it needs to be aligned at a page boundary or something else so that the DMAs can actually happen effectively. Now, why is this? Because the DMA hardware is intentionally kept relatively simple, right? Things like, can I use an address of 3 for a 32-bit word? Well, no, not really, right? It has to be a multiple of 4. The address of the 32-bit word has to be a multiple of 4. So using an address like 3 would sort of lead to an alignment issue, right? It's not that it's completely wrong, it's just that it's misaligned. We already know about alignment from C programs in general because they don't allow us to store ints and so on in a non-aligned manner. DMA would definitely struggle with things of that sort because you do not want to complicate your hardware by bringing in the requirement to handle all these alignment related issues. Now there is an advanced form of DMA which is called scatter gather, where you could potentially have a scenario where because the size of the buffers that you need is so huge, it's several megabytes perhaps, that it's not really feasible to allocate contiguous buffers. Remember what I said about contiguous buffers? It's one continuous set of memory addresses in the memory. The way that the actual OS kernel handles memory is that it sort of, if necessary, allows it to fragment. It finds wherever there are chunks of free space and make sure that they all get clubbed properly through an appropriate translation level. Now DMA can't handle address translation, but what it can do is it allows you to use a number of smaller buffers and ring them together or connect them together into some kind of a chain, right, where each buffer essentially has a pointer to the next descriptor, which is basically a struct of this sort, right, which says, okay, once you have filled up this particular buffer, why don't you go and start filling data in the next location out there. So all of these buffers have already been allocated. They may be contiguous one after the other, or they may not. The fact is DMA doesn't care at that point, right? It just sort of fills each one with the appropriate amount of data and then moves up. That allows you to handle basically much larger buffers, especially when you have to deal with fragmented memory. What that also means is there is this notion of so-called zero copy, right? Zero copy is important because what it says is there can be scenarios, especially let's say when you are trying to transfer data from a program, let's say a browser, you have filled out a form, you click submit, it needs to transfer all that data into a packet and send it out on the network, right? Now you have a copy of that sitting inside the browser's memory. I need to now take that and then copy it into the driver memory corresponding to the Ethernet, and then from there into the actual the peripheral address itself. Now why do this multiple stages of copying? Potentially I should be able to just point at the address in the user space itself, right, if everything else has been taken care of and I don't have other security related issues, right. There can be scenarios in which I would prefer to avoid that copy. Now the problem is, because that original buffer was almost certainly allocated with some kind of a fragmented malloc kind of approach, it means that I cannot do a direct sort of DMA transfer. I need to give it a series of descriptors pointing to all the different fragments of the memory and then tell it, okay, do a transfer from here. So zero copy can be done with these kind of scenarios. Well, what I gave was a slightly contrived example, but it turns out that zero copy helps to avoid a lot of unnecessary copies and can be useful in many contexts. Now the device tree integration, I am going to just put it up here and leave it at that. Typically what you would have is the FIR filter itself, right. The main thing is that it would basically mention that yes, there are these DMA connections out here, and the DMA itself would say that yes, I need to have the different capabilities like MM2S, S2MM and so on, because the driver needs to make sure that it's able to actually sort of process all the kind of functionality that is required for this. The important thing of course is that the DMA needs this interrupt, right. Apart from that, it needs the compatibility string to show what kind of driver is there. The FIR filter potentially could even be something which no longer really requires an address space because there is not much to configure, but assuming that you want to sort of send your registers, your coefficients and so on into it, it still makes sense to have a driver which can accept the memory map, MMIO based way of updating things like coefficients, which may not really require the high throughput of DMA. So to summarize, right, DMA basically allows us to offload bulk transfers from the CPU. There are a few things that you need to keep in mind. DMA memory allocation has to be done in such a way that you keep cache coherency in mind. The way that it is used is that you typically configure the address and length and then just wait for the IRQ, which means that your driver needs to respond appropriately when the IRQ happens. As we saw from the examples, typically you get higher throughput than MMIO, especially for moderate or large buffers, right. And for applications like video, network, high-speed A to D conversion and so on, it is essential. It is not really optional because this is the only way that you can get close to maximizing the bandwidth that the bus is capable of. So once again, key takeaways from what we have discussed so far. In the context of polling, For example, in the case of the FIR filter, I would be writing data one by one into the filter, waiting for the filter to complete and then reading data back. My CPU is pretty much fully occupied, but it has the least latency simply because the overheads are very low. I'm just basically writing the data I need, I don't have any extra functions. The CPU is sitting there in a tight loop waiting, and as soon as it's done, it basically moves on, right? But the throughput is going to be low. Interrupts, the CPU load is less because while the FIR filter is working, the CPU can go to sleep, right? But the actual transfer itself is going to be somewhat, it's going to be more or less the same complexity as the polling approach. The latency over here would be more than in this case because I need to wait for an IRQ and then respond to it. It would also usually have a low throughput. Whereas DMA is precisely meant for scenarios like streaming, especially when you have a relatively large number of samples. Once again, keep in mind these numbers, as we saw from the examples, are dependent on the actual time taken for MMIO transfer, DMA setup and so on, right? So the final choice of what is the correct approach to use over here would depend on how much data, the rate at which you are processing, and whether or not you care about the CPU being kept busy at any given point in time.